Good day, my dear students. We are continuing with our differentiation. Specific objective. At the end of the lesson, the student should be able to find higher derivatives of some functions and then find the derivatives of composite functions. More on differentiation. The function y is equal to f of x such that the f of x is defined as ax raised to power n down the line is actually called the polynomial of nth degree. There are some other functions like trigonometric functions, logarithm functions, exponential functions, etc. We talk about the derivatives of some functions as summarized in the table below. You recall why this is y, which is a function of x. Here is the derivative of the function with respect to x. So where y itself is equal to a constant, which is a number or a known quantity, the derivative of y with respect to x becomes 0. As we have been saying, that the derivative of a constant is 0, but when y is equal to x, the derivative of y with respect to x becomes 1, and if y is equal to ax, the y the x is a, following differentiation from the first principle. Then the derivative of sin x is cos x. Down the line, we go like this. But one good thing about the exponential function is that if y is e raised to power x, which means y is equal to exponent x, the y the x remains unchanged. This is logarithm. That y is the logarithm of x to the base e. That's the meaning of this. The y the x becomes 1 over x. And if y is a raised to power x, the y the x becomes a raised to power x log a. The difference between this logarithm and this logarithm is that the base of the logarithm here is exponents, but the base of logarithm here can be any number, including the exponent itself. So when you view the functions, you view their derivatives, the first derivatives to be precise. So we say, what we have achieved so far is called derivatives of y with respect to x, the first derivative of y with respect to x. The first derivative of y with respect to x is just the first differentiation that you did. It means therefore that we can equally have second derivative, the third derivative, and so on this note. We understand that some functions like the polynomial functions are continuously differentiable, bearing in mind that the derivative of a constant is 0. Because of this, we think about going into what we call the higher derivatives. That is, after differentiating a function, can we differentiate it again? We say, given y to be equal to 5x raised to power 3 plus 2x squared minus 8x plus 12, the first derivative of y with respect to x, remember differentiating from the first principle, Multiply the coefficient by the power, subtract 1 from the power, so that 3 multiplying 5 is 15. We do the same thing here, and we get that the first derivative of this particular function is 15x squared plus 4x minus 8, which is the first derivative of y with respect to x. If we want to differentiate it again, it means the second derivative of this particular function, which remains the first derivative of the first derivative. It is called the squared y, the x squared. It means differentiate this again. If we differentiate this again, we get 30x plus 4. We can continue differentiating until we don't have anything to differentiate again, which now reads that the second derivative of y with respect to x, which is also called the squared y, the x squared, is 30x plus 4. It simply means differentiate this. If we differentiate this again, we get this, which means third derivative of y with respect to x. Following the first principle, the derivative of 4 will automatically be 0 because it is a constant, as you already know. Now that the third derivative is already 30, there's no x here, so if we try to differentiate it again, we get 0, which is in line with the agreement that the derivative of a constant is 0. So it means that once this is differentiated 4 times, the last result will be 0. For a polynomial like this. So how many times did we differentiate it to get something that is different from 0? It is the number of times we have the highest power. I mean, the magnitude of the highest power will determine that one, but it is not always true. Because if this function is a composite one, another thing may come up. We keep going. The second one, we are giving y to be x raised to power 4 plus x squared plus 6. The first derivative will give us 4x raised to power 3 plus 2x. The second derivative means the derivative of the first one to give us 12x squared plus 2. The third derivative gives us 24x, and when we differentiate this to get the fourth derivative, we get 24. You can see we have differentiated 4 times this power 4, and we have gotten something different from 0. Immediately we exceed this highest power, the derivative becomes 0. Okay. We talk about composite functions. We say a function of the form y is equal to f of g of x, where both f and g are separate functions of x that may or may not be the same, is called a composite function. It means f composition g of x. It can also be called g after x. That's the meaning of the composition of the function. Let's see what it will look like. We talk about derivatives, which is the differentiation of composite functions. We say if y is a composite function, which is a composition of one function to another, then the derivative of y with respect to x becomes the f, the g, multiplying the g, the x. It can also mean the y, the u, multiplying the u, the x. It means that y is a function of u and u is a function of x. So we go ahead. Example. Here we are given that y is equal to the sine of 3x squared plus 7x minus 7. Already we know that when y is equal to sine x, that the y, the x is actually cos x. But here we have a complete function here, which we can replace by u, saying that u is equal to, taking that u is equal to 3x squared plus 7x minus 9, so that the journey can be easy. We can therefore simply write that y is equal to sine u, so that the job will not look bulky. Following the formula, which says that the y dx, which is equal to the y du multiplying the u dx, it means that we are going to find the derivative of y with respect to u first. So it means differentiate this. We then find the derivative of u with respect to x. It means differentiate this. We multiply the result to get what we are looking for. It means when we differentiate y with respect to u here, for y is equal to sine u, the y du becomes cos u. For u to be equal to 3x squared plus 7x minus 9 du dx is 6x plus 7, following differentiation from the first principle. Result, we multiply this by this to get the y dx. So we carry on. Still defining the y dx to be equal to the y du multiplying the u dx, we already got our the y du to be cos u and the u dx to be 6x plus 7. We multiply, u cannot multiply all these things. So in this type of multiplication, a polynomial multiplying a trigonometric function, please drop 1, especially the polynomial function, before the trigonometric function so as not to cause confusion. However, it is important to put certain things in brackets. So this multiplying this is also this multiplying this, since multiplication is commutative but not always true. Because in multiplication of matrices you may not get it commutative. Okay. So our final result now becomes 6x plus 7 in a bracket multiplying cos u. But what is u? U has to be replaced because we took u to be 3x squared plus 7x minus 7. So we can remove u and return what it was. As a result, our dy dx becomes 6x plus 7 bracket multiplying the cosine of the already given function. Carry on. Another example, we are given y to be equal to 5x minus 8 raised to power 4, so we can easily remove 5x minus 8 all raised to power 4. We can easily put u for 5x minus 8. We therefore say y is equal to u raised to power 4, meaning therefore that u is 5x minus 8. So if we differentiate this, we are going to get 4u raised to power 3, which is this. But we have already taken u to be 5x minus 8. When we differentiate this, we can simply get 5. And upon multiplication of values, we shall multiply this by this to get 20u raised to power 3. What is u? U is 5x minus 8. So return it at the end to get that the y, the x, is equal to 20 into 5x minus 8 raised to power 3. Here we have another one again, that y is exponent a whole of this. 3x raised to power 4 minus x raised to power 3 plus 9x squared plus 21x minus 29. What we have to do is to write that y is equal to exponent u, that's e raised to power u, meaning therefore that u is a whole of this power. So the derivative of this with respect to u is simply e raised to power u, which is exponent u, knowing that if y is equal to exponent x, the y dx still remains exponent x. Don't worry, when you come back to class, when we shall expand, give you the expansion of, an expression that represents exponent x, you will know the reason why the differentiation of y with respect to x still remains what it is under the exponential function. So we have seen u has been taken to be equal to 3x raised to power 4 minus x raised to power 3 plus 9x squared plus 12x minus 29, differentiating from the first principle, which says multiply the coefficient by the power and subtract 1 from the power, we get this again. Recall that we are working on composite functions, of which the derivative of y with respect to x is the product of the y du and du dx. So we multiply the y du by du dx to get our final result. Having gotten it like this, we recall that u is something, return what u is. U is 3x raised to the power 4 minus x raised to the power 3 plus 9x squared plus 12x minus 29. Don't say it is long. It is not long. Just do the right thing. Are you okay? Then after this, I want you to read, work. What do? What you have to do is there any advantage? Is this particular differentiation useful for anything? Whether your answer is yes or no, check on the maxima and the minima of functions, and then the applications of differentiation, and wait for us in the next class. Thank you, my dear students. God bless you.